Welcome to physics, the physics of electricity and magnetism, and all the things that you can do with electricity and magnetism. You know it's all around us, but we're getting into the details. So as you embark on studying electricity and magnetism, I want to just give you an overview of what you're going to do, and then we'll go through it again and again, layering in the ideas. Perhaps the difficulty in electricity and magnetism is things are not as tangible as when you pushed carts up inclines and you had strings attached to them and such. But you can still get a feel for it using the old physics. So we've got to use the old physics. And for most people, they need to review it as you do. So kinematics, we are going to do some simple descriptions of motions. Some circular motion is a big deal with magnetism and so on. So we've got time, we've got displacement, we've got velocity and acceleration, and we've got angular stuff, so stuff that is going to be spinning around. So you'll need that. A big part of this course, though, is force analysis, and we're going to see in a similar way field analysis, electric and magnetic fields. We need to do free body diagrams. There's torque involved. So all that stuff does get used and you're expected to know it or review it as you go. So the good news is the framework of physics stays the same when we have these new applications. We've got momentum analysis, linear momentum, mass times velocity, angular momentum, rotational inertia times angular velocity, impulse. That is not going to be used very much in this course. Perhaps a little bit at the end, touching on the fact that waves have both energy and momentum. But we will use it sometimes. Energy analysis is huge, huge. It's how we do circuits and things like that. So this is maybe the most important, as is often the case when you have lots of objects interacting. So energy analysis. So in addition to that, from our mechanics course, we're going to remember mass and still use it. Objects can have mass. We saw that mass is two things, right? Inertia, and creates and feels gravity. Right? So it's two different things. So objects have mass. And of course, somehow that mass creates and feels this force of gravity. And we can talk about what happens in terms of the pull of gravity. So it's interesting to note that gravity is always a pull only. And that's going to be different for electric and magnetic forces. You can talk about it since it's conservative, which is to say that if gravity slows me down, or slows the pen down, it'll speed it back up. It gives the energy back. So we think of it mathematically in our heads as taking the energy and storing it in a bank, the United Bank of Gravity, and then giving it back to the kinetic energy. That's how we think of it. We know, in fact, what's happening is that the force is a pull, so as you go opposite the pull, you decrease speed, and as you go with the pull, you increase speed. So the potential energy of gravity, that idea, we still are going to use sometimes. I do want to make a note, though, that many times we're talking about things on an atomic scale, and in that case, we often don't have to worry about gravity. Yeah, gravity's here, but when you're doing an electric circuit, you don't have to worry about the gravitational effects on the electrons and things like that. So you just have to know when to use it and when not to use it. So we'll talk about that. Okay, so that's the old framework that we're going to use, and you'll see how we use it. And again, I want to make a note on the new. The new stuff, what's going to be tangible and what people studied are the forces of electric force and the magnetic force. And the weird thing here is that the electric force can push something away, but it can also pull. That's different than gravity. And a magnetic force, different. Magnetism is not electricity. We will see that it's connected, but it wasn't known. Magnets can also push and pull. So that adds a layer of complexity in our mathematics as well. So we'll see that. What's not tangible? So in order to describe this, and I want to give a historical context here, that we are talking about around 1800 to around 1900. Exploring these ideas. People didn't know. So you might say Galileo, early 1600s, say 1600. Newton, late 1600s, say 1700. And people started studying things. They kept doing stuff and making better telescopes and doing all kinds of things. They were wondering, what are we made of? What's going on here? And that's a tricky question. As they explored, which we'll talk about in the next video, explored these pushes and pulls, they were able to come up with better and better equipment. Thank you, engineers. Better and better experiments. Thank you, engineers, for that equipment. And dig deeper and deeper and find out the relationships. And so they came up with these concepts called electric charge, which we can use a lowercase q or a capital Q. We'll talk about that in the next video. But it's kind of abstract. Electric charge. That bugs me, just like saying masses, that bugs me. We'll see why. It's okay if we know what we're talking about. Electric fields, capital E with a vector because there's a direction associated with it. And, you know, the complexity there is the complexity of any vectors. You've got to use coordinate systems and trigonometry and break things down into components. Magnetic fields. What creates electric fields? What creates magnetic fields? We use B, I think probably because there's just too many M's, right? So there is an M that shows up too when you study the magnetic fields inside of materials. You know, there's letters galore and they overlap, so whatever. And there's a guy named Bobiot, and you'll learn the Biot-Savart law. So B for magnetic fields. What else is not tangible? Well, really atoms, if you think about it. I mean, people didn't know that there were atoms. Things that are inside of the atom, subatomic particles. You know what an atom's made of. Protons and neutrons in the nucleus, electrons going around, sort of. But you can smash those and break them into even smaller things than that. So subatomic particles, most commonly, protons, neutrons, electrons. But it turns out there's other stuff too. It just doesn't last very long. It's not around much. But it's all, electrical stuff is fundamental to us. It holds us together. It holds us together, and you're going to study that. In studying this through that period of time, there was a realization about what makes electric fields and what makes magnetic fields. And those laws were summarized in the 4 Maxwell equations, which is what I have written right here. And God said, and what is the punchline? And then there was light. Because if you take these 4 equations and you can write it in integral form or in derivative form, if you take those equations and put them together, you get the equation of a wave. And the speed of that wave is the speed of light. And so it turns out that electromagnetism and electromagnetic waves are in a sense tangible. They're hitting me right now. They're bouncing off. I'm absorbing. I'm radiating. Somehow light is connected with atoms. Atoms absorb light. Atoms create light. So that's an interesting connection. And so you're going to study that. And it's going to take you about 4 months to get into it, doing all kinds of little problems, and you'll see those connections. So hopefully that is exciting. But again, when I say not tangible, another word would be abstract. And that's part of the difficulty people have. You know, I can think about friction like this, I can feel it. But this stuff is kind of weird. Actually, it's made up. And people were wondering, is that just a tool to analyze things? Interesting thing is that with these relationships, we find out that the electric and magnetic fields take on a life of their own, namely light. So there's something deep there. But it's a new kind of idea. We'll talk about that later. Then we're going to, as we study this, we're going to look at how it's applied. Because while this is all cool in theory and useful in theory too, we do use it. And allow us to make better equipment, which gives us better experiments, and we'll deeper and deeper and deeper into the nature of things, and how we apply things looking at different materials. What's the atomic structure of different materials? Some of them conduct electricity, conductors. Others don't conduct well, insulators. Then there's something in between, semiconductors. And really, it's a whole range of the ability for materials to allow electrons to flow through them. We're going to put together circuits, which of course there's wires, and with wires, I should put wires in there, right? Wires, which are conductors. And we can connect batteries. So we've got batteries here. Like, how does that work? I know it's a battery, but how does it work? It's a chemical process, and chemical processes are electrical processes. Chemistry is about electricity, except if you try to figure out all this stuff to do chemistry, you'd be really slow. Just use the rules of chemistry and you figure out what reacts with what. So batteries, power supplies, they can make electrons flow through wires. Resistors can reduce the flow, so maybe you don't want as much electric current resistors, and that's just different materials. So if I have different material, here's a these are different resistors, and instead of a wire, if I send it through here, it'll reduce the current to whatever I want my application, whatever my application needs. So variety of resistors, carbon-based composites often are, and you kind of make it like a rough surface so it resists just like friction would. So it kind of looks like that. Capacitors, C, or two plates. You can have capacitors. There's all these little things here that are capacitors. What do? They also store separate. So in our last video that we're going to splice together here, the battery ran out. Well, that's perfect. You can't get away from it. Lights bouncing off, you cannot get away from electricity. Laptop, right? It's all around us, right? So how do we make basic? So you got to work on basic circuits. Maybe you've done that, maybe you haven't. If you haven't, get in there and start doing it. And we're trying to imagine or visualize electrons going through the wires, and it'll help it to become more tangible, at least in your mental image of it. So capacitors, what we do is we transfer electrons. So we build up electrons on one side, and we take electrons from the other side to build up the electrons on one side. They can look like all kinds of things. If this is charged, don't put your tongue across there or your finger across there. You can get quite a shock. And so even when something like a laptop is not plugged in, there can be capacitors, and it can be very dangerous to stick your hands back in there. You can get quite a shock because they can build up quite a lot of, you can say, electric potential energy. You could say they can build up a lot of electrons, separation. We can do variable capacitors, all kinds of cool things, right? And we have inductors, it looks like a spring, doesn't it? And that has to do with a coil of wire, kind of like this, or even like a slinky. We can put those in circuits, and we'll see what those do. Capital L for inductance. One of my favorite units, the Henry, which is just cool. We can have direct current constantly going one way, right? Often with a battery. Or we can have alternating current going back and forth. Either way, you can get the job done. If you want to warm your hand, you can keep going the same way, or you can go back and forth. You're still going to warm your hand, or light the light bulb, or whatever you do. There's electric motors, which in reverse are electric generators, so you'll learn about those. Yeah, transformers. How do you take high voltage and step it down to low voltage, or low voltage and step it up to high voltage, and what's the cost? How do you do that? Again, these are the basic designs. In actual engineering, you take that up and look at other design elements of heat transfer, material cost, weight, etc. For those designs. So it's kind of cool. And all of that requires the theory of electromagnetism. Okay? And depending on what you do, you'll need more or less of it. It's a good idea to have the basis of circuits. So, as we say, this is a big topic, but it's connected, it turns out. People found that out in those 100 years. So inch by inch, life's a cinch. Yard by yard, life is hard. Little by little, keep going round and round, and it starts to make some sense. The glory is in the details, and the details for us come out of the math. One critical relationship that you're going to need to use is writing something in derivative form and versus integral form, the same relationship, which we've seen that before with potential energy and conservative force, for example. And of course, algebra and trig and all that stuff. So that's what we're embarking on, studying all this cool stuff that's around us and been taken to a very high level that we want to get at least up to the 1900 point in our realization, which, by the way, in studying all this led to a transformation. You get better and better equipment, more subtle phenomena, and right around there, you have the birth of crazy stuff. Relativity, special relativity, general relativity, warp space-time, quantum mechanics, the nature of atoms, pretty nuts. So this is a wonderful story of human exploration. It's a powerful story because it gives us things that make life warmer, safer, more fun, and it's also a powerful knowledge set so that you can go on and be an engineer and make the next improvement to whatever it is you do. So hopefully you enjoy it. We're going to try to make these non-tangible things a little more concrete, again with the conceptual framework first, and then you'll get into the applying the math and the other techniques. So I hope you enjoy it.